All right, so Snell determined all of this. I'm not going to go through how the law was derived, but Snell's law, or the law of refraction, is what it's called. And we can talk about it as waves moving from one medium to another, where they have a wavelength, velocity, and frequency, a wavelength, velocity, and frequency in the second medium. And we have an angle of incidence and our angle of refraction here. Okay, what you need to know from this is the actual law itself here. So sine theta 1 is equal to lambda 1 over lambda 2, v1 over v2. This isn't directly on your formula sheet, so we do need to take a look at it. It does say on our formula sheet n2 is equal to sine theta 1 over n1, and that's sine theta 2. We don't deal with the n's in this class, so we won't be using that, but we can use it to equate to our other formula. N2 over N1 is equal to V1 over V2, which is equal to lambda 1 over lambda 2. So because these are equal, we can say that sine 1 over sine 2 is equal to these. So that's how we get the formula from our formula sheet. Now, this means that any part of this formula can be equals to each other. So this fraction could be equal to this fraction could be equal to this fraction, or this fraction can be equal to this fraction. Remember, we're only going to be using two at a time here to solve for some unknowns. So a water wave traveling in deep water at 15 meters per second enters a shallow region with an angle of incidence of 30 degrees. If the angle of refraction is 22, what is the speed of the wave in the shallow region? So we have initial values and final values, or we could say we had deep water and shallow water. Either way, just keep your numbers organized between the two of them. So our initial angle of incidence is 30 degrees, and our angle of refraction was 22 degrees. The initial speed was 15 meters per second. We are looking for the final speed here. So we're going to use our Snell's law formula. We don't need wavelength, so we're not going to include that part of our fraction. So we're going to say that sine theta 1 over sine theta 2 is equal to v1 over v2. Subbing in, we have sine of 30 degrees over sine of 22 degrees is equal to 15 meters per second all over v2. This is just something where we can cross multiply and divide. So multiply both of those numbers and divide by whatever sine of 30 degrees is. So rather than reorganizing to solve for v2, you can just cross multiply and divide in our equivalent fractions. Making sure that your calculator is in degrees, not radians. If you're in Math 30, cross multiplying sine of 22 degrees times 15 meters per second dividing by sine of 30, we get that v2 is equal to 11 meters per second. Example 3, a wave travels from a region with a speed of 45 meters per second into a region with a speed of 60 meters per second. If the wavelength of the wave is 1.5 meters in the slow region, what is the wavelength in the fast region? So we have a slow, which is our initial, into a fast region, which is our final. It had a speed of 45 meters per second in this region, and its final velocity is 60 meters per second. The wavelength has a wavelength of 1.5 meters in our slow region. We are looking for the wavelength in the fast. So we are going to use V1 over V2 equals lambda 1 over lambda 2. Because we don't have any angles here, we don't need the sine portion. Okay, subbing into our formula, we have 45 meters per second over 60 meters per second, which equals 1.5 meters over lambda 2. cross multiplying and dividing, we get that lambda 2 equals 2.0 meters. All right, so we've talked about reflection, we've talked about refraction, we're going to talk about diffraction now. So in the diagrams to the right, we see what happens when waves meet different kinds of obstacles. So in diagram A here, when water waves pass through blades of grass, the waves reform around the grass. So the waves are traveling this direction here. The wave hits the blade of grass and it seemingly has a gap. However, once it continues, it reforms itself after this blade of grass. Same thing on our log here. For a stick in the water, the waves reform around this stick. Again, waves are traveling in this direction here. We see the waves coming in kind of whole. It hits the stick and it has a gap. However, a couple waves after, it seemingly closed that gap again. Same thing with our log, but it seems to take a little bit longer the larger this object is. We have our waves coming in, it hits the log, and the log seems to block them. However, the waves slowly start to come together here after the log. And then, so this was a short wavelength. This is a long wavelength passing the log. It seems to have a longer wavelength, and so when it passes through the log, it takes fewer troughs or crests to mesh back up again. They're much closer after 2 wavelengths than it was over here after, it looks like 4. So the apparent spreading and bending around of waves around corners and around obstacles through openings is known as diffraction. So the bending and spreading of waves. So this guy developed a principle to explain diffraction and other wave phenomena. His principle says every point on a wavefront may be considered to behave as a point source for the new spherical waves generated in the direction of the wave's motion. What? Okay, so our wave started from a point source back here. And that's what created these waves. What they're saying is each point on our wave could generate other waves. Okay? And it will generate as a point source again the same wavelength. So notice that this is the same distance in this case, and it'll continue to ripple out at the same rate. Okay. So in the case of an obstacle, the wave front can bend around the edges of the obstacle by sending out new wave spherical fronts in the edges of the obstacle. So our wave is traveling in this direction. We see the wave kind of flat here. And as soon as it hits here, we would expect that it would not continue in this way. However, this point can be a wave front, so it can be a point source for another wave. And then that wave continues in this direction. Okay, so this part came from this point source, and these are just continuations of our initial wave front. Okay, if we have waves moving towards kind of this gap where there's a barrier here, remember we will have a point source, and that can be the kind of radiation through. So we can have our point sources creating more waves, starting our wave again. The diffraction of waves and diffraction through a slit is a really good example of this. You could technically try both of these experiments in a tub of water, creating some waves where we have an object that can't bounce up and down, maybe something very heavy sitting in a tub of water, and you would see the waves bend around that object or through a slit. Okay, interference. As we saw with one-dimensional waves, when two waves meet, they interfere. Okay, remember we saw this when we had a wave coming in this direction and in this direction. If we have two waves that their crests meet, they will be amplified into a large wave, and when we have a negative and a positive wave meet, they will be interfering completely with one another. Destructive interference. Okay, the same thing happens when we have two-dimensional waves. So if we have this situation where two sets of waves are being generated at the same time and in the same phase, okay, meaning same wavelengths, etc., and where they meet is important. We'll talk about that. So we have a wave being generated from this point here and from this point here. And you can just see these are like the ripples coming outwards. So the darker space will be our trough and the lighter space is our crest. All right. So our two waves are rippling out and we can see that they start to overlap here. And we need to kind of draw some lines, I thought, to make some sense of things. So I drew my lines on my crests, moving outwards from my waves. Okay, so that's the crests from one wave, and then we have the crests from another wave moving outwards as well. All right, what we can see is when two crests meet, it becomes an even brighter white spot. So I'll just erase in that moment here. And you can see that it becomes even brighter. And that's because we have two crests adding together. And we get what is called an antinode. Okay, so these, when crests meet crests and troughs meet troughs, constructive interference occurs, and these are called antinodes or maxima. So we have that here where a crest meets a crest, but we also get this where a trough meets a trough. Okay, so in between here, our very darkest spot will also be considered a node. Sorry, an antinode. It's harder to see, I think, out here. All right, where a crest meets a trough, this is where we get destructive interference. So we have a crest and a trough coming together, and that's where we get our destructive. And that will be our node. Our antinode, remember, is a crest and a crest, or a trough and a trough becoming larger. This one will just become flat. All right, the nodes happen, again, where a crest and a trough meet. So something like this, or here. And so that's where we go to kind of the lightest gray. So an antinode is the really bright spot or the really dark spot. Our nodes or minima happen at like a medium gray, if you will. Okay, so these kinds of spots in between. All right. Let me just highlight that in the blue. So when a crest meets a trough, complete destructive interference occurs, and these are called nodes or minima. So notice that the pattern of antinodes with nodes in between them refer to Pearson. So we have our nodes here, and in between them are the bright spots. Or we could look over here and we have our darkest spots. And in between those will be our nodes. Lots to think about there. So to understand how an interference pattern is produced, consider the diagrams below. two waves of wavelength lambda, so the same wavelength, are shown to originate from two vibrating sources, S1 and S2, with a distance of d apart. While waves spread out in all directions, we'll focus on the wave trains shown here. So we know that, of course, these are going to continue in big circles, but we're just going to focus in one kind of plane or one direction. In diagram A here, the waves travel the same path length. When they meet, they are in phase, meaning they are crest to crest or trough to trough. Okay, this means we have constructive interference occurring, resulting in a maximum or an antinode, which is like a minimum. All right. Okay, so how to tell is that they have, again, the same wavelength, and when they get to one point, they are at the exact same point in their wavelength. All right, so our amplitude is going to double here, or they'll be added together. In our second example, we can also have, destructive interference. Okay, so if the path difference is one wavelength or a whole number, we can also have, constructive interference here. So this wavelength has started before. So we have one wavelength before, and then they continue on in the same fashion. And so they'll have the same number of wavelengths afterwards. So this could be one wavelength, but we could also have multiple. So maybe we had 5 wavelengths before, and then we have another, I don't know, let's say this is 10 wavelengths together afterwards. The total path of S2 is 15 wavelengths, and the total pathway of S1 is 10 wavelengths. However, they meet at the exact same point in the end. And so we will have our constructive interference where they add together. If the path difference is a half wavelength, or basically it's not a full wavelength, if they are off by only a half or something less, or like a fraction of it, they do not line up. So in this case, we've started our wavelength, and S1 starts after we've got halfway through. So we are not at the exact same point when these two start. So we have a half a wavelength, and then say we go 10 wavelengths afterwards. So S1's total path is 10 wavelengths. S2's total path is 10.5 wavelengths. So when they meet, one will be at a crest and the other will be at a trough. And so we're going to get destructive interference. So to determine this, we just need to find out how many wavelengths fit in each of these. And if they're both whole numbers, we know that it'll be constructive because they will end up adding together. And if one is a whole number and one is like a half or a fractional wavelength, then we are going to get destructive interference. So looking at our first one here, A. So we have points S1 and S2 are sources of identical water waves. Point P is some distance away from the sources. The distance P to S1 here is 80 centimeters, and the distance S2 to P, my mistake, is 90 centimeters. Describe whether this is constructive or deconstructive interference if the wavelength in A is 5 centimeters. Well, let's look at path PS1. If the wavelength is 5 centimeters and our total distance is 80 centimeters, our wave can repeat itself 16 times. So what I did is I said, okay, I'm going to take my total distance and I'm going to divide by my wavelength. And I get that there are 16 waves or repetitions, if you will, of the wave. Then I'm going to do the exact same thing for distance P to S2. So I'm going to divide our 90 centimeters by the 5 centimeters, and I find that I can get 18 repetitions. That means that 2 waves happened before and then S1 started. So because they are both whole numbers, the wave will fit perfectly, if you will, into that length and will be at the exact same position, either crest or trough, when they meet. Therefore, this is constructive. If we look at B, where our wavelength has changed, let's look at PS1. So I'll divide the distance that we have, so our 80 centimeters, centimeters, divided by our 20 centimeter wavelength. That means I can fit 4 waves or repetitions into that space. If I look at PS2, I have 90 centimeters divided by our 20 centimeters, and I get 4.5 repetitions. That means that if we started here, S1 was at this point when S2 was at this point when S1 started. So it will be going into a trough as S1 is starting at a crest. Therefore, because the wave from S2 will be halfway through, its wave will just, it'll be in the opposite position, if you will. So these are destructive wave interference. Okay, so a half repetition isn't good. If we are in a full whole number, they will be adding together nicely.